I'm going to look at example 5 now. We're going to find the limit as x goes to infinity and the limit as x goes to negative infinity of these two rational, or of this rational function. We're going to find these two limits. It's the same rational function. And once again, I'm going to use the graphical approach to try to find these. I could use a numerical approach as well. It would just take me a slightly longer to explain. So I'm going to graphically find these limits. This rational function has kind of a unique graph. It has kind of a hump around the x value of 0. And then as I zoom out, notice what's happening. As the x value gets bigger and bigger and bigger, the y value on this graph is also increasing. As the x value gets smaller and smaller and smaller, the y value is also getting smaller and smaller and smaller. It's decreasing. So what does that mean for our limits? Well, it means that as x goes to infinity, the function's value is also going to infinity. Remember that going to infinity is the concept of getting bigger and bigger and bigger. The same thing for negative infinity. As the x value goes to negative infinity, the y value also goes to negative infinity. It gets smaller and smaller and smaller. In terms of the limit of these, we would say the limit as x goes to infinity is infinity. The limit as x goes to negative infinity is negative infinity. As far as horizontal asymptotes, what we would say is that there is no horizontal asymptote here. No horizontal asymptote, because neither limit as x goes to infinity or limit as x goes to negative infinity gives me a real number. So since I don't get a real number, there's no horizontal line that our function is approaching. So there's no horizontal asymptote in this case. Now, the obvious question is, why did this one not have a horizontal asymptote, but this one had a horizontal asymptote of 3, and this one had a horizontal asymptote of 4, and this one had a horizontal asymptote of 0. All of these had limits as x approached infinity and x approached negative infinity. And they were all rational functions. So what's unique about these? Well, if we take a look at the difference between the top polynomial and the bottom polynomial, in other words, the polynomial in the numerator versus the polynomial in the denominator. When our polynomial in the numerator was a smaller degree than our polynomial in the denominator, then our denominator grew much, much faster than our numerator. And so if the numerator is essentially standing still and the denominator is growing, then this fraction is getting really, really close to 0 as x approaches infinity. Similarly, as x approaches negative infinity. In this example, we had our numerator and denominator both be of the same degree polynomial. And if you look at what the limit was as x goes to infinity and as x went to negative infinity, this was 4. Notice that 4 is just 4 divided by 1, those are the coefficients of the biggest term, biggest degree term. The same thing was true here. The limit of r of x as x approached infinity was 3. We have polynomial divided by polynomial of the same degree. And if we look at the ratio of the coefficients, we get 6/2, which is 3. In this last one, this example 5, our numerator had a higher degree than our denominator. And we ended up having our limit as x approached infinity go to infinity. We can generalize this observation by looking at the following result. So we look at the limits of rational functions at infinity. At infinity means as x goes to infinity or as x goes to negative infinity. So here's the rule. If we have a rational function, polynomial divided by polynomial, let's let the numerator polynomial, p of x, be degree n with leading term an x to the n. And let's let the denominator polynomial q be of degree m with leading term bm x to the m. If they are of the same degree, then the limit of the rational function is going to be given by the leading term's coefficients, namely the coefficient a sub n divided by the coefficient b sub n. Now I said b sub n, you might say, well, didn't this say m? Yeah, but n and m are the same numbers. So these are b sub n is the leading coefficient of the denominator when n and n equals m. If we have the same degrees, we just look at the leading coefficients. If the bottom degree, or excuse me, if the bottom polynomial has higher degree, then the rational function is going to go to 0 as x goes to either plus or minus infinity. And if the numerator has higher degree, then the rational function is going to be infinite as x goes to plus or minus infinity. So that's how the limit as x goes to plus or minus infinity is going to work for all rational functions. I do want to explain a little bit about why that's happening as we look at a couple of the problems that we have already done. So let's take the limit as x goes to infinity of this rational function, the one where we had x to the third plus 4 divided by 5x squared plus 5. We already found that that limit was infinity. So why did it have to be so? Well, it had to be so because x to the third grows a lot faster than 5x squared. At really, really high values for x, if one of our numerator or our denominator is growing faster, then that one is going to take over. By taking over, what I mean is this fraction is basically the top is growing really, really fast, and the bottom, well, compared to the top, it's growing really, really slow. So we got a fast growth over a slow growth. And if the top is growing faster, then we're going to go to infinity. Now it's just the opposite if you flip these around. If you have a really slow growth on top and a really fast growth on the bottom, then we're going to be going to 0. Well, what's going to happen when they're growing at the same speed, when both are x squared speeds? Well, when x squared speed is growing, when we're growing at the x squared speed, then if you look at the individual terms, the ones that are going to take over and dominate are going to be these largest degree terms. In other words, as x goes to infinity, this minus 5x plus 9 portion is essentially going to not contribute much. Remember, these are really, really big values for x. And the minus 49 is not going to contribute much as we have x going towards infinity. And so this limit just becomes essentially limit of 4x squared divided by x squared, which you can cancel like terms, cancel the x squareds, and get 4. Now you can only do that as x goes to infinity. If this were like x goes to 5, then obviously you can't do that. This only works when x goes to infinity, because as x goes to 5, these things approach real numbers. As x goes to 5, these things approach real numbers. So it only works thinking of these limits that way when we think of the limits as x goes to infinity or as x goes to negative infinity. That is the reason why we can find the limits of rational functions at infinity. Once we know this, then we can find these limits really, really quickly. So what I'd like you to do is try these two functions. Find the limits as x approaches positive infinity and as x approaches negative infinity of f of x and of g of x.